In this video I will show how to solve question 2 from the linear regression handout, where we will analyze a dataset to find the Herbert Pirt parameters of a lactic acid producer. We are given a dataset of the biomass-specific rates of substrate, lactic acid, glycerol, carbon dioxide and oxygen for different dilution rates from a chemostat experiment. Using this information, our task is to find the Herbert Pirt parameters A, B, C and MS. Thus we have 4 unknowns. The biomass-specific rates have been determined for 5 different dilution rates. We can fill in these datasets in the Herbert Pirt relation to obtain 5 equations. Remember that the growth rate is equal to the dilution rate in a chemostat. So we can fill in the growth rate and the biomass-specific substrate, lactic acid and glycerol rates in the Herbert Pirt relation. We do not use the biomass-specific carbon dioxide and oxygen rates. Let's write it out. As we have 5 equations and 4 unknowns, we have 1 redundancy. We can write this linear system in matrix notation by defining the vector of the 4 unknowns, which we will call beta. Now we can write out our matrix A and a vector Y by filling in the data. We can find the vector of unknowns beta with this formula. Remember that AT means the transpose of matrix A, which means that the column and row indices are switched. In this case, calculating A over B would result in the same answer. However, hereafter we will take into account the standard deviation, thus we will need to use this notation. So let's now find our vector of unknowns beta. Let's start by writing out the dataset. I will already separate the columns for our convenience. In this section I will define all the parameters as underscore QS, as we will later on define them again, taking into account QO2 and QCO2. We will now define matrix A. The command 1 size mu will make a vector of 1s with the size of mu for the MS column. We can also define vector Y as the measured biomass-specific rates and calculate the vector of unknowns beta with the given formula. Remember that in MATLAB, transpose is written as a quotation mark. We have now estimated the Herbert Pirt parameters from the dataset. Question B asks us to determine the accuracy of the parameters that we have just determined. Therefore, we want to calculate the covariance matrix beta as beta as a result of the error in the measured specific substrate rate QS. We know that the standard deviation of QS is 0.05, a homoscedastic error. Remember that the covariance is the square of the standard deviation. Thus we can write out the covariance matrix of QS. We use the derivative of beta with respect to y, also called the Jacobian matrix, to calculate the covariance of the parameters as beta. The square root of the diagonal gives us the standard deviation of the Herbert Pirt parameters. Let's first define the homoscedastic error in QS as 0.05. Now we can define a covariance matrix of QS using this notation. Then we can calculate the Jacobian matrix using the provided formula and calculate the covariance matrix of beta, the Herbert Pirt parameters. If we take the square of the diagonal, we obtain the standard deviation of the Herbert Pirt parameters. Take care of the dots before the square. Let's display our findings nicely with a number to string notation. We have now found the accuracy of the Herbert Pirt parameters. We can see that the standard deviation is more than 1000% for each parameter, which is extremely inaccurate. So, question C asks us to take into account the oxygen and carbon dioxide measurements to get a more accurate estimation of the Herbert Pirt parameters. We can include the oxygen and carbon dioxide measurements by expanding the matrix system. In the exercise, the relations between QO2 and QCO2 and the Herbert Pirt parameters was derived from the metabolic stoichiometry. We can recognize our unknowns in these relations. Let's start by expanding these relations. We can now separate the known and unknowns. We will separate the knowns on the right-hand side of the equation and the unknowns on the left-hand side. Now we can write this in matrix notation by separating the vector of Herbert Pirt parameters beta. We can then write out the matrices A for O2 and A for CO2, as well as the vectors Y for O2 and Y for CO2. We can now combine the three matrix systems of the measurements QS, QO2 and QCO2 to calculate beta, taking into account all of the measurements. We can combine them by stacking the A matrices into one matrix, as well as the Y vectors. This way we obtain one matrix system. Now we can estimate the Herbert Pirt parameters taking substrate, oxygen and carbon dioxide data into account by calculating beta. Now we also want to know how much the accuracy improved. We know that the error in the O2 and the CO2 measurements is 0.05. Thus we can construct a covariance matrix for QO2 and QCO2. To take into account all errors, we have to combine the covariance matrices of QS, QO2 and QCO2 like this. Thus we obtain this covariance matrix. Now we construct the Jacobian matrix and calculate the covariance matrix of beta. The square of the diagonal of S beta is the new standard deviation of the Herbert Pirt parameters. So let's first define the A matrix for the oxygen measurements according to the stoichiometry, and the Y vector as well. Now we can define the homoscedastic error of 0.07 and define the covariance matrix of QO2. Let's do the same for CO2. We can copy the O2 definitions and adapt it for CO2. We can now calculate the Herbert Pirt parameters including all three measurements. Therefore we will stack the A matrices of QS, QO2 and QCO2, as well as the Y vectors of QS, QO2 and QCO2. Thus we can calculate beta to obtain the new Herbert Pirt parameters. Next we are interested in the accuracy of our estimation. Therefore we will stack the covariance matrices using the notation block diagram. We define the Jacobian matrix and calculate the covariance of beta. The square of the diagonal gives us the standard deviation of the Herbert Pirt parameters, taking into account substrate, oxygen and carbon dioxide measurements. Let's display our outcomes nicely again. You should notice that the standard deviation is smaller than when we only took into account the substrate measurements. However, it's still quite inaccurate, as the standard deviation is still about 300%. We could for example improve it by adding the glycerol measurements to the estimation.